Hey everyone, we're back for lecture 23 about implicit numerical methods that we kind of left off with last time. So last time we talked about numerical methods in general, the Ford, Euler, Hume's method, and Runge-Kutta. And we said these are all backward methods. And so the convergence of those methods depended on the H that you used. And so at the end of the last lecture, we said what we'd like is methods that we knew converged for any value of H. And we said implicit methods were methods like this. They were always stable. So let's build two implicit methods in this lecture. We'll build backward Euler and we'll build the implicit trapezoid method. So let's remember the problem that we left off with last time. So this was the differential equation, second order. It happens to be a model for a mass spring. And it had an exact solution here. So just to refresh our memories, if we run a Ford Euler approximation with an H of 0.05 up until a time of 10, we get a curve that looks like this. It's hard to see the approximation of the exact, but in the color in your PDF, it should be clear. I think the dots are red. If I change the step size to be twice as large, this very quickly does not converge, right? This is, you look at the exact solution, this is exponentially decaying. So obviously the numerical method is unstable. So that's a problem. So if we remember, we were trying to solve a differential equation. Let me see, I haven't seen later pages of the notes. The differential equation that we were trying to solve when we discretized it looked like yk plus 1 was equal to yk plus this integral. What's the integral? Let me find it in the notes. Oh well, okay, we'll see it a little bit later in the notes. But the idea was that we were trying to approximate an integral. And all of these methods, oh, here it is. Here's what we're trying to approximate, right? All of these methods are really, how do we approximate this integral? So the backwards methods, we're doing an approximation that we would call backwards, say where we used, if we were trying to approximate the area under a curve, we discretize the area into like a bunch of rectangles. So it looks like this. We have rectangles. We say, what's the height of the rectangle? Is it, do I take the height as like the functional value on the left-hand side or the right-hand side? And so for all the backwards methods, we've been doing left-hand side, this kind of smaller number, if this is an increasing function. So for implicit methods, let's start to look at the right-hand side rule. So instead of approximating the value of, say, that the rectangle that you would use to draw the area under the curve, let's do the right-hand side kind of endpoint. And so when I do that, I get a discrete time update that looks like this. Here's the issue. So this is what we'll call the backwards Euler update rather than forward, but it has yk plus 1 on both the left and the right-hand side. So yk plus 1, what we usually solve for, is implicitly defined, right? This is an implicit numerical method, and we may not have an explicit solution for this. So we do have some cases where we do have explicit solutions, and solving for yk plus 1 is possible. So let's consider this special case. If I have a linear system that looks like this, then the update for backward Euler becomes this. I can solve that explicitly, right? I subtract the hayk plus 1 onto the other side, and then I multiply by the inverse of this matrix. And then I get an update formula, right? This is actually a backward Euler update formula for a linear system. So I can do an example where I solve this, right? So let's find, I have y naught as 1 minus 1, and I have this a, what should y1 be? y1 should be I 1, 0, 0, 1 minus h. We said is 1/2 times a 0, 1 minus 2 minus 3. I want to do that inverse times y naught. Oops, times y naught. So what should this be? 1 minus 0, 0 minus 1/2, 0 minus plus 1, and then 1 plus 3 over 2, so 5/2. Is that right? Yeah, that looks okay, right? So this inverse times this. What does it give me? I don't know, some number from MATLAB. We'll go to MATLAB super quick. I'm going to share MATLAB. Share. Okay. And so I want to do 1 minus 0.5, 1, 5/2, so -1 times 1 minus 1. And I got some number here, 2/3 minus 2/3 for my vector. Okay, so I get solutions like this. Obviously, I can write this in a code and do it a bunch of times until I think I've converged, right? Or until, not until I think I've converged, until I've done it for the amount of time that I want to do it. Okay, so let's see what that would look like. So this just says, let's go back to this and look at the numerical solution. So if I, now remember for forward Eulers, if I used h was 0.1, this was a problem. Now with backward Eulers, say I'm going to do h is 0.2, not a problem at all. And coding this is really similar to the forward Eulers coding, which you maybe have looked at when you looked at lecture 22. Hopefully I put the M file and the code should be written in the notes. I'll just share the MATLAB screen with you one more time. Here. Here we go. So this is the code that I've uploaded for this lecture. If I look here for the backward Euler algorithm right here, down here in my list of functions here, BE linear, because now I input the number of steps, step size, initial condition, and now I'm using A, because I'm already assuming it's a linear differential equation. And then I initialize my time and my state Y, and then update time by adding H at every time step, and update Y by multiplying by an identity matrix that's the size of A minus HA inverted times the previous Y. So pretty straightforward. When I do that, I get a plot like this, and I see, yeah, backward Euler looks like it's stable, looks like it's converging to the exact solution. The code is right here for you to see, but where is it stable? Is it stable for all H's? That's the question, right? So let's do the same thing that we did for forward Eulers to compute the H's that will give a stable solution in this case. So just as a refresher, when I have the continuous time case here, A has two eigenvalues, -1 and -25. So the equilibrium solution, which is at 0, 0, is asymptotically stable, right? Because I just need, in continuous time, that both of my eigenvalues are less than 1. So the exponentials decay. When I move to discrete time, in this case, the condition that I now need is for the eigenvalues of this guy to be in the unit circle. That's what convergence means in discrete time, right? So the question is, when are the eigenvalues of this in the unit circle? So continuous time, I need the eigs of A less than 0, and in discrete time, I need the eigs of I minus HA inverse to be norm less than 1. okay? Because they could be, well, I guess they're just numbers. Okay, so let's just check that. So just remember how we kind of can translate eigenvalues, right? So if I have an eigenvalue that I know of A, if I know how that relates to the eigenvalues of I minus HA inverse, inverting means I do a reciprocal, and then I shift by 1 for the identity and multiply by minus H for that factor there. So when I have lambda 1 is minus 1, that means 1 over 1 minus H times lambda 1 is 1 over 1 plus H. And I know that this guy is always going to be less than 1. Less than 1 for all H, because all of the H's are positive, right? It's always going to be dividing by a number bigger than 1. Similarly, lambda 2 is 25. I have 1 over 1 minus H times minus 25, otherwise known as 1 over 1 plus 25H, which is always less than 1. Or I should say always less than 1 and greater than 0, right? It has to be in the unit circle for all H that are positive. So that means the question is, for what values of H is this fixed point asymptotically stable? That means Y star 0, 0 is asymptotically stable for all positive H's. And that's why these methods are called unconditionally stable. It doesn't matter the H I put in. That said, doesn't mean that it's super accurate, right? It looks like decent, but you can see places where visually I'm not on the curve. And so we actually have another implicit method that is more accurate. So let's take a look at that. So let's get back to this integral that we're trying to solve, right? This is what we were looking at previously. When we were doing the Euler method, we were just approximating the area under a curve with a rectangle. But if you remember from your calculus class, you can also approximate it with a trapezoid, right? Trapezoid, well, instead of doing just the left-hand side or the right-hand side, I can take the average of both. Think of it as a trapezoid. So in terms of the functional values, that means I have f at tk and yk plus f at tk plus 1 and yk plus 1 divided by 2, the average. And so I can use that kind of formula to write the implicit trapezoid method. Again, if it's just a general f, this is implicitly defined, and since I have a yk plus 1 here, I can't in general solve for it. But if I have a linear function, in this case, then I can, right? Because the right-hand side now becomes yk plus h, and then a times yk plus a times yk plus 1 divided by 2, the average here. I can solve that for yk plus 1, right? I subtract h over 2 times a yk plus 1 over to the right-hand side, and then I multiply by the inverse of that matrix, and I have this other matrix that multiplies yk, right? An identity from here and h over 2a from here. And so I get this formula here. This is called the implicit trapezoid method. So let's see. If I have this initial value problem again, and I want to choose an h equal to 1, can I carry out one step? Sure, right? So y1 is going to be I, so 1, 0, 0, 1, minus h over 2, so 1/2 times a, 0, 1, minus 2, minus 3, inverse times this with the plus, times y0, minus 1, 1. Okay, so what do I get for that? We can go over to MATLAB, share the screen with you again. So a is 0, 1, minus 2, minus 3. And I want 2 by 2 identity minus 0.5 times A to the minus 1 times the same thing with a plus times 1 minus 1. And I got some numbers which are different than in the last case. Maybe closer to the exact solution, although not necessarily what I'm concerned with for this example. So yeah, pretty straightforward how we plug this in. Let's take a look for the example that we've been doing. We'll plug it in, not just look at one point here, not y1. Let's take a look at a bunch of time values. So same differential equation as we've been doing before. Now I'm going to approximate it with the implicit trapezoid, right? So just visually, as compared to the backward Euler, this looks better, right? For backward Euler, I could actually visually see the mismatch between the exact solution and the discrete approximation. So this is looking much better. Encoding this is no more complicated than coding backward Euler, right? The exact same code here, but now I multiply this guy by some other matrix, right? The identity, whatever's in the formula. And that'll be the MATLAB code for you to see. So great, that makes us think maybe implicit trapezoid is a different order than backward Euler. But let's first, before we take a look into that, let's just confirm that this also is a method that works for any value of h, right? So just like backward Euler, and because this is an implicit method, it's what we call unconditionally stable. So again, same system here, same eigenvalues. Now I have this difference equation for implicit trapezoid. So what are the values of h that will give an asymptotically stable fixed point for the discrete time system? So when lambda 1 is minus 1, we know we are looking for what? 1 minus h over 2, lambda 1, 1 plus h over 2, lambda 1 on top, right? Those are going to be the eigenvalues of this differential equation. When I plug in minus 1, that means I have 1 minus 1/2 h over 1 plus 1/2 h. So when I plug in a positive h, the denominator is always going to be bigger than the numerator, right? So this is, let's rate it as belonging to the set 0 to 1 for all h positive. Is that true? For all positive h's. Let's see. Let's take a look. Oh, and actually, while we're at it, let's write out what we should have for lambda 2 is minus 25. So in that case, I have 1 minus 25 over 2 h, and then 1 plus 25 over 2 h. Let's plot these guys in MATLAB. So let's plot these guys in Mathematica and see what we see. So I'm going to share the screen with you. I guess I need to wait for Mathematica to open. Share. Okay, so h, we need a range of h's. Well, let's just say we're going to plot this function. So 1 minus h divided by 2 in the numerator, and then 1 plus h divided by 2. I'll make that bigger for you to see. Okay, and I want to plot that for h going from 0 to 10. So it's always between 0 and 1, right? As h gets really, really big, it's going to approach -1, but it's looking always good. Yep. And then the same thing if I put a 25 on top. 25. Same thing. Okay, great. So that means these guys always live from 0 to 1 for all h positive. So again, unconditionally stable. This algorithm works for all h's, which makes it incredibly powerful because you don't have to worry if you see something blow up that it's, you know, you see solutions kind of go to infinity, that it's about the stability of the algorithm. It's not. It's about, it would be about, you know, the values you're actually trying to approximate. Great. So the last thing we want to do is just compare these methods. Visually, we saw backward Euler looked, you know, not as good approximation as implicit trapezoid. Let's see why. So we use MATLAB to do this conversion study that we did the last time, also for forward Euler and for Humes and Runge-Kutta, right? So what we want to look at is we want to look at the difference between the exact value and the approximated value for two different parameter sets, either for some h's like 0.005 or 0.0025. So half of that for the same amount of time. And then look at the ratio of the error with the exact solution with these two different h's. And what we said is if that error looks like 2 to a certain power, that power gives you what we call the order of the algorithm. So in the notes here, I have the code that we use for computing these. So I'm just running my BE linear algorithm in both cases for the parameter set that we said here, 2,000 time steps and 4,000 time steps and so on to go up to 10 with a step of half the size. And I take the difference between what I compute with the numerical algorithm and then the exact solution here, which is two-dimensional. So y exact, no y dot exact, same for E2, and then I take the ratio of the errors. And what I get, as it says in the text here, is 2.0092, which suggests that backward Euler is what? It's going to be 2 to the 1. So it's first order. On the contrary, when I do the same convergence study for implicit trapezoid, my output is 4, which implies that implicit trapezoid is, so it's 2 to the 2, so second order. So that supports that the figure that we saw, just for this one example, looked more accurate. It is indeed a more accurate algorithm. Not that much harder to compute also. So yeah, so that's all we have to talk about for today. Okay, bye.